let's use what we've learned now about converting to cylindrical coordinates to try to solve for an actual volume. So in this particular case, what we have are two surfaces. One is z equals 2x. And what that is that's a plane, right? So if you think about the line z equals 2x, it's just a straight line. But since there's no y component, it stretches infinitely in both directions along the y-axis. So you have that just planar surface. And then you also have this z equals 2x squared plus 2y squared. And what that is that's an elliptical a paraboloid. It's really not elliptic, it's really circular because those numbers are the same. So what you're going to have is these concentric circles that are paraboloids. So on the zx axis, it's a parabola. On the zy axis, it's a parabola. But then if you were looking at it top down, it would just look like a bunch of circles stacked on top of each other. And so what you have is a plane leaning over and then a parabola striking it. And then this is in the zx plane. You have a parabola. But then as that parabola sort of curves around, it's going to hit the plane. So it sort of curves around and hits the plane. This isn't the best drawing ever, but the blue plane and the red paraboloid are intersecting there. And then there's this purple area. And what that is that's the projection of the intersection. So where the paraboloid intersects the plane forms you're going to find is the projected area is a circle, but it forms some sort of boundary region. So we have to solve for all of these things. Now we could do this in rectangular coordinates, but we'd have to think it through. The integration, in my opinion, is more difficult to do in rectangular coordinates. And so let's use cylindrical coordinates to solve for this. So anyway, to do this, we need to get a few concepts. We need to find bounds for theta, r, and z. And it looks like our z bounds are pretty well solved for, right? It's bounded above by the plane and below by the paraboloid. But the problem is these are not in cylindrical coordinates. So what we're going to find is z equals 2 r cosine theta, right? Because x is r cosine theta, y is r sine theta, and r squared is x squared plus y squared. So if you look up here, if I factor out a 2, what I also find is z is 2r squared. So these are our lower and upper bounds, or rather our lower and upper bounds. And so that's going to be the way we set up our integral for in z. Now we have to figure out what our r bounds are. Well, as shown here, there's some sort of intersecting region. And in those intersecting regions, what you'll find is that the z value is the same, right? If they're on top of each other, we know that their z values are the same. So if their z values are the same, we can use these equations and say, where are these equations equal to each other? So two r cosine theta is equal to 2r squared. If we divide both sides by 2r, we're making the assumption that r is not 0. Then what we get is r is equal to cosine theta. So that is, if you think about that, that's the equation of if we were drawing a polar graph, if you go all the way back to your studies there, if you have something in the r theta plane, r equals cosine theta has the graph that looks like a circle in the its rectangular representation is that x minus 1/2 squared plus y squared equals 1/4, which is actually what happens if you solve for this in rectangular coordinates, right? It shifted. This point is 1/2, 0. It has a radius of 1/2, and anyway, but this is the polar representation. R is equal to cosine theta. So the reason that I mentioned that is because if you look on this projected circle, at any given point, R goes from 0 to whatever cosine of theta is. If theta is negative pi over 2, R doesn't go anywhere. If theta is positive pi over 2, R doesn't go anywhere. If theta is 0, R goes all the way out to 1, but it has some sort of fall off there. So what we're seeing is that our bounds for R are 0 up to cosine of theta. And then for the theta bounds, again, we look here, what we see is, if you think about the xy plane, and we have and we're, right, this is the xy, this is positive y, that's negative y. The theta is only going from negative pi over 2 to positive pi over 2. And that's all we need to consider for that. So, given the fact that theta is going from negative pi over 2 to positive pi over 2, R is going from 0 to cosine of theta, and Z is going from 2R squared to 2R cosine theta, we have our bounds. Remember, everything, the bounds here can depend on things go backwards, but as you go back, eventually you can't have things depend on it, right? If this thing had a Z in it, it would be improperly formed. If this thing had anything but constant numbers, it would be improperly formed and impossible to solve for. So this can depend on anything going backwards, this can depend on that one, and so on. And if you get into iterated integrals of like 8 dimensions, which doesn't happen often, but just remember that sort of ordering matters. So anyway, if we're doing volume, our function that we integrate is a 1, and then we have an R. In this case, it looks like a dz, dr, d theta. So what we need to do now is we need to integrate. So I have R. Well, we're integrating with respect to z, so R is a constant. So what we end up with is negative pi over 2 to pi over 2, 0 to cosine of theta of RZ from 2R squared to 2R cosine theta dr d theta. And when we sub in for Z, what we get is negative pi over 2 to pi over 2, 0 to cosine of theta, 2R squared cosine theta minus 2R cubed dr d theta, right? We just sub in for Z. Simple enough. Now we want to continue on. We're integrating with respect to R. So we go from negative pi over 2 to pi over 2. The antiderivative here is 2/3 R cubed cosine theta minus 1/2 R to the 4th from 0 to cosine theta d theta. Now what you find is when R is 0, these terms vanish. When R is cosine of theta, what we end up with is negative pi over 2 to pi over 2, 2/3 cosine 4th theta minus 1/2 cosine 4th theta d theta. 2/3 minus 1/2 is 1/6. So we now have 1/6 negative pi over 2 to pi over 2 cosine 4 theta d theta. So we need to use the expansion here. So let's go over to the side and do the expansion real quick. cosine of the fourth theta is cosine squared theta times cosine squared theta. And cosine squared theta is 1 plus cosine 2 theta over 2. 1 plus cosine 2 theta over 2. If we factor out the 2's, we get 1/4. 1 plus cosine 2 theta. 1 plus cosine 2 theta. Which gets us 1 plus 2 cosine 2 theta plus cosine squared 2 theta. So then we have to expand that again. 1/4, 1 plus 2 cosine 2 theta plus 1 plus cosine 4 theta over 2. Now with a little bit of algebra, we can rewrite that as 1/8 3 plus 4 cosine 2 theta plus cosine 4 theta. So now that we know that, we can go back to what we had before. We can pull out when we take the antiderivative, we pull out the 1/8. So we have 1/48 3 theta plus 2 sine 2 theta plus 1/4 sine 4 theta from negative pi over 2 to pi over 2. Well, the nice part is when I plug in pi over 2 here, that's sine of pi, that's 0. That's sine of 2 pi, that's 0. When I plug in negative pi over 2, that's sine of negative pi, 0. Sine of negative 2 pi, that's 0. So these terms actually vanish. So what I have is 1/48 3 pi over 2 minus negative 3 pi over 2. So what I have is 1/48 3 pi, which is pi over 16. So that's a lot of work for pi over 16. And I'm done solving this, so you can cut the video off if you want to, but I want to point out something here. I got this from Larson Calculus ebook. And it's just a problem in there. I believe it's in the section 14.7. I think it's number 15 or 17. And in that problem, this is not the answer. In that problem, the answer is pi over 6. And I struggled with this. I worked on this problem for like 5 hours because I was like, they can't be wrong. There's no way they're wrong. Well, it turns out they are. And the reason they're wrong is because they didn't do this in cylindrical coordinates. And that's not the reason it should be wrong. Because it shouldn't matter if you do it in rectangular or cylindrical coordinates. And so but if you do this in rectangular coordinates, then what you find is you have to set up an integral of the square root of 1 minus t squared or 1 minus x squared. It doesn't matter. But the point is that you end up with the square root to the third power. And if you neglect the power of 3, if somehow you omit it, you do something wrong, right? You just solve it incorrectly, you end up with pi over 6. But I struggled. I kept getting pi over 16. I didn't know why. Didn't trust myself. And it turned out that what I had done is I had made the same mistake in rectangular coordinates. And I want you to see something. If you look at all this stuff here, there's pretty much no way you're going to get pi over 6 from pi over 16. You'd have to have some really weird fraction you're carrying, which frustrated me because it means that even though the problem in the book was telling you to do it a specific way, the person who came up with the solution didn't do it this way. So be careful. Don't be afraid to say the book is wrong. Ask somebody else, work with somebody else, solve it. Took me a while, but finally found that I finally trusted my answer for a couple of different reasons. So don't over or undersell yourself. Make sure that you are are solving the problem the way you're supposed to, and anybody can make a mistake, even a textbook. So that's all I got for this.